C of messing with magnets, it's on electromagnetic induction. And if you remember back to the earlier lab, the wired lab, we had a current moving through a wire and it induced a magnetic field, caused the compass to deflect. And if the direction of the current changed, then the deflection of the magnet changed. Well, it turns out that the reverse is also possible. If you move a magnet around, there's an electric field induced around the moving magnet. If you move it near a wire, then there's an electric current induced in the wire. If you coil the wire, then that current is concentrated in the wire. And if you coil it multiple times, then you get the picture. So, if you look at part 1 of part C, it says inducing an electric current. And I have the setup already made. There's a coil of wire hooked up to a galvanometer, which is able to measure a very, very small amount of current. And first, if you look at moving a bar magnet into the coils, note what you see. See the reverse of direction? So this would be an alternating current. Now, what if I take the compass, the magnet, and move it all the way through? What will happen to the direction of the deflection? Did you get that? Let me try it again. So one direction, and then as the south pole of the magnet comes through, the other direction. One direction, the other direction. So see the alternating current. Now, how efficient of a motor would this be, or a generator? Not very efficient. So actual generators, they actually spin the magnet and around the coils. And they're not bar magnets, but they're differently shaped magnets. All right. Now, the next thing we're going to do is inducing a magnetic field. So we have the same basic setup with the opposite direction of what's going in and what's coming out. So I have a coil of wire. It's enameled wire. It's coated so that the current can go through without conducting to the nail, just as this was insulated as well. And then instead of moving the magnetic field, we're going to induce a magnetic field. We're going to move a current through the wire. So all we need is a battery. So now we have the battery hooked up, and we have a nail, and we have something made of metal, iron, steel. And just to show it's not a magnet, then as soon as I complete the circuit, it is a magnet. Then as soon as I undo the circuit, not as soon as, but shortly thereafter, it's no longer a magnet. And then it is a magnet. And notice the magnetism lasts for a little while. In fact, that's how they make bar magnets, is with a piece of iron, and then they put a coil around it, and then they run an electric current through the coil, and it induces a magnetic field in the bar magnet. And then they also sell devices that are similar that can recharge a bar magnet once the magnetic field has dissipated enough to not be useful. All right, the next section says inducing an electric current. And all we get doesn't seem possible. The only thing we get is an extension cord. I thought you needed a coil and a magnet. Let me think. Oh, there's a ready magnet available anywhere on Earth. Right, it's the Earth's magnetic field. So what we're going to do is take this and put it on the floor, and then we'll see how coordinated my camera person is. He's going to have to move the extension cord and film the galvanometer at the same time. Place bets. How is this going to work? I don't know. Let's see. Next part of electromagnetic induction has us trying to induce an electric current in an extension cord. And I know what you're thinking. Oh, let's just plug it in. No, that's cheating, because the current is then coming from someplace else that's doing all the work. So we have to move this coil, this extension cord, through the magnetic field of the Earth in such a way that it induces an alternating current. What could we do? I know. Let's play jump rope. We're not actually going to play jump rope. If somebody were here to jump, we're just going to move the coil this way. And then if the cameraman will now show the galvanometer. All right, so there's a close-up for you to be able to see the alternating current. Ta-da! Electromagnetic induction. Isn't that fun? Times have I said, and this is the last section, so there's two more sections. One, you're on your own. It says, make two general statements about the relationship between electricity and magnetism. I'll give you a clue. It has to do with how one type of field can induce the other type of field, and vice versa. Okay, so generators and motors. Hook up a small motor to a battery. So if the cameraman will zoom in on the motor, I will hook up first the red lead and the black lead, and wow, the motor goes as soon as I hook it up. What do you know? An electric motor spins when you put a current through it. Now, what if we reverse the process? What if we move the motor and put it up to a meter? Can we get a current from the motion of the coils and the magnets inside the motor? Make a prediction. What do you know? Ta-da! Electromagnetic induction. It's fun. It's physics. See you next time.